Hello, thanks for joining us at the Charge Virtual Conference on EV Engineering. The topic of this session is the key factors of hairpin stator impregnation, and it's brought to you by Technofirma. There'll be a Q&A session after the presentation, so click the Q&A button on your screen to submit your questions. And please welcome our speaker for this session, Dario Geraci from Technofirma. Welcome.
Hello all, welcome to the webinar, The Key Factor of the Hairpin Stator Impregnation, Theoretical Model and Real Application. My name is Dario Geraci. I've been with Technofirma for 12 years and I'm the responsible for sales for Impregnation Business Unit. Let's see the agenda. After a company introduction, we will briefly talk about the target of the impregnation and what means impregnation. Then, starting from theoretical model of the capillarity, I will introduce a theoretical model applied on the hairpin geometry. By means of this new theoretical model created and verified by the experimental data, was being analyzed the key factor that play a significant role in the capillarity phenomenon. Let me introduce a Technofirma company, which is a private-owned Italian-based company with its own three divisions: painting, washing, and impregnation. With more than 70 years of experience, 120 employees, more than 1,000 plants worldwide, and with a 40 million revenue. Our presence worldwide, the headquarters is located in Monza, in the north of Italy, where is done the engineering phase, R&D, final assembly, and machine testing. The manufacturing is done in our two manufacturing plants located nearby our headquarters. And Technofirma has a global presence in terms of sales and service. The biggest service points are in China, in Beijing, in US, in Detroit area, and in Germany, in Cologne. So let's start to talk about the impregnation target. Impregnation increases the electrical insulation of the motor, provide mechanical strength, provide environmental resistance, improve the heat transfer, and remove the air inclusion. So in other words, the target is optimize the global performance of the electrical motor and extend the life of it. But what means quality on the hairpin and how to achieve and what are the main parameters responsible to get that? So in the following presentation sheet, we will try to answer to those questions. An impregnation process is theoretically perfect if all voids inside of the slot before of the impregnation are completely disappear at the end of the process. Normally, to check the success of the impregnation, the simple way is to perform a destructive visual inspection test, cutting the two heads and if possible, remove the slot or analyzing as indicated in these pictures. Analyzing the slot is possible to define a number called fill factor, that is the percentage of the resin available on the total space available. The fill factor is a very important value normally used to define the impregnation quality. The problem of the filling is a matter of capillarity. But what is the capillarity? The capillarity is defined as the ability of the liquid to penetrate into fine pores and crack with wettable walls and be displaced from those not wettable ones. So this phenomenon is a complex mixture of different contributions and depend on many different parameters, such, for example, liquid and solid surface tension, the contact angle, the solid roughness, and density and viscosity of the fluid. Starting from the Lucas-Washburn equation concerning the motion of the liquid into a capillary tube, is indicated here on the right side, we can analyze the relation between time and distance. We can immediately see that there are a contribution of pressure, summatory of P, here, and we have an atmospheric pressure that can be considered zero because the capillary is open from both sides. We have the capillary pressure and hydrostatic pressure. R in the formula, in the schema especially, R is the radius of the tube, eta is the viscosity of the fluid, epsilon is the coefficient of slip. If we substitute the value of P, of pressure, inside the formula, we obtain the following equation. If we do some assumption, for example, epsilon equal to 0 in case of wettable materials, or horizontal capillary, so the angle is 0, and as I mentioned before, 0 as the atmospheric pressure, we obtain the following formula. And if we integrate that, we obtain this relation, where we can see that the time required to travel the distance into a capillary of radius L depend on the square of the distance through a multiplicative constant that depend only by the geometry and the liquid property. So time and distance are linked, and there are also a constant dependent only by the geometry of the system. If we take in account the real geometry of the system, the capillary could be considered no more a circular section, but rectangular one. And rectangular with very flat and large. So we can consider space between two flat parallel plates with the width much more longer than the distance between them. Okay, so h in our schema is the distance, can be represented the distance between two copper bars. L represent the length of the stator in our hairpin geometry. So rearranging the formula, we obtain this one, and integrating this equation, we obtain the following formula. If we substitute the delta P value, so the summatory of the pressure, we obtain the formula indicated here, and we can immediately understood some important points. So we see that time and distance are still still the same relation, but what is different compared to the equation we saw before is the multiplicative constant. And it's very clear that the distance between a parallel plate, okay, H, play a fundamental role in this phenomenon. So the liquid flow is much much slower when this gap is small. So now we already immediately answer why in the hairpin trickling, or anyway in the hairpin varnish application, normally is required a very long time compared to the traditional one. Okay? It's because of this matter, because of the space inside of this geometry. In order to obtain experimental data to be compared with the theoretical value from the equation saw before, an experimental setup like the one represented here has been done. We place three enamel bar in two parallel glass plates with a distance that was kept constant between the bars in order to simulate the real geometry of the hairpin. So we consider 170, 290 microns, and so on. And then the bar was fixed in a sandwich geometry using a second laboratory glass plate. A metallic holder keep in the proper position the entire structure. And was possible also to angle this platform in order to make a different tests according to different angle. Between the lower glass and the platform, we put a sheet of graph paper so we could see the progress of the raising during the entire experiment. We record the time and distance of the raising during the application, and the same data was being estimated by our formula and then was being compared. The two curves in the graphic show that the formula that are very close. So the formula we think for the hairpin geometry is correct, is validated by the experimental data. For sure, in the real hairpin geometry, there are many other factors that can, let me say, have a contribution on the penetration. But for sure, we can consider the previous equation as a good starting point to do some analysis. So, analyzing this formula, we can define which are the parameters that play a role into the penetration phenomenon, but especially we can divide it in parameter under film control, so under varnish equipment supplier control, and some other under customer control. So under technofirma control, we have a viscosity of the liquid, time of the application, and capillary angle. From customer control, we have age, the distance between the bars, surface tension, so the materials of the copper bars, or to better say, not the material, but the coating on the copper bars. L is the distance, so it means the length of the stator. Then there are some other parameters that we can consider constant, as the gravity or density or the height of the liquid source or the contact angle between liquid and solid surface. Analyzing one of the most important parameter under our control, one of the most important is the viscosity, for sure. Viscosity has to keep in the right range during the entire application. Here we have an example of one typical impregnation product used the e-mobility market, Voltatex 4200, and the relation between viscosity and temperature. So in the machine, it's very important to keep the rays in the right range. And how to do that? By thermoregulation system and also preheating the stator in the right at the right temperature. Here we summarize a typical impregnation process that is normally done by preheating, application, gelification, curing, and cooling. The important parameter we can control is the time of the application. We saw before that time and distance are there is a relation. So in order to obtain the full penetration, especially in the longer stator, is required long time of application compared to the previous impregnation process on the one-wire design, where typically the impregnation process was very short. For the hairpin, the time is increased a lot, and due to the increasing of time, we have another effect that must be controlled, that is the temperature of the stator, because long application time means that significant temperature drop down during the application. So to solve this problem, we in our equipment, our solution permit to divide the resin application in different steps. Here we indicated only two, but could be more, and place in the middle of each step of application an heating up of the stator. In this way, we permit to refill the right condition, to have the right viscosity that we saw before, and give the right driving force to the resin to continue the penetration. Otherwise, if the resin, the temperature of the stator drop down, the driving force due to the viscosity, the resin will be stopped and will not reach the complete entire penetration. Another parameter is the tilting angle, because here is very easy to understand that there is a contribution also for the hydrostatic pressure. We have a minus sign here because we are considering capillaries inclined downwards, so the angle is negative, but also the sign is negative. So at the end, this value is positive. So this value reduce the time. So this contribution is going to reduce the time or is going to increase the length. Looking to the other parameter under customer control, we can see the most relevant are the copper bar distance. This is very important. The length of the lamination, the surface tension due to the coating of the material, coating of the copper. It could be enamel or could be PEEK, but also some other as the type or shape of the paper, for example. Here we have an example, a specific case where the distance between bars represented here was not respected only in one, only on two bars because was bended, probably because there are some benefit for the state of manufacturing to bend just some of them. But for the impregnation point of view, in the points where the edge is too close, the driving force is zero. So there is no penetration, the resin is stopped. Okay? And this is the reason why. So taking in consideration all those information concerning the process, we develop a dedicated solution expressly designed for the hairpin. Is indicated here only one single module. And in this module, we have a possibility to manage the tilting angle, for sure the viscosity of the liquid, but also to manage time of the impregnation. This machine is very flexible concerning the process, concerning the time of the application, because the stator could be heating up during the application anytime we need. So we can divide the entire application in different steps and have any intermediate temperature thermal recovery we need. In this case, also for the long, for example, more than 20 minutes or more than 30 minutes for big and heavy stator, we have a possibility to fill completely the slot. This line that we call modular, that is the latest development, could be supplied as a standalone module or could be supplied as a high production volume in series. In that case, the preheating and curing and cooling are moved outside because normally it's not required to have, it's not necessary to have a part in rotation. So we leave only the core of the process inside the module as the trickling application, thermal recovery, and gelification. To summarize, we can say that the capillarity depends on a key factor from supplier side and some other from customer side. Only sharing the information concerning the stator at the beginning of the project, so a co-design between supplier and customer will permit or will guarantee to get a high quality impregnation. Otherwise, if some of the parameters discussed today are not considered previously, it's difficult then to obtain the good result. So this is a real suggestion to all customers that is attending my presentations. Co-design, share the information could make the difference. Thank you very much for your attention. I'm now available to answer to your question.
Thank you for the presentation. Now we'll begin the Q&A session, so please submit your questions by clicking the Q&A button on your screen. I see we have a few questions submitted already. If you could begin by reading the question aloud, that would be great.
Yes, there is a question from Mr. Geron. Isn't the first applied resin already gelling in the slot during the heating up of the stator, again before you do the second step of resin application? So this is a good question. For sure, during the heating up, the intermediate heating up is very important to avoid to reach the gelification temperature. So normally, for this kind of resin, monocomponent resin, the gelification point start at 140 degrees. And so we need to stay below that temperature. And normally we preheat at 120 degrees. Then there is another question concerning which insulation paper design and shape is preferred for impregnation. Okay, for impregnation, normally the O shape is the favor design because there are no barrier inside that could let me say stop the capillarity, and the O if possible to have the O shape with the overlapping in order to avoid some resin flow into the internal diameter. I don't see some other question. I already answered, Jeremy, to another question by written. Maybe I can take again. What type of resin is utilized in these channels for the presentation? So in our presentation, in our test, it was used Voltatex 4200 because it's one of the most used, but also some other resin with the same same type. Like, for example, Elantas UP 142 has the same behavior. That's all. I don't see some other question.
Okay. Well, Dario, really appreciate your presentation, and any closing remarks? Anything else, Dario? Any other closing remarks from you, Dario?
Okay.
All right. Well, that concludes this broadcast. Thanks to Tecnofirma and Dario for presenting and everyone for attending. That's it. Thank you.